The concept of partial pressure is likely something you've learned some years ago, and partial pressure tells us about gases and the amount of a gas that I have in a particular situation. The most common is to think about the gas, for example, in the atmosphere. In the atmosphere, we know that we have oxygen and we have nitrogen. The total pressure in the atmosphere at sea level is 760 millimeters of mercury. And when we discuss the partial pressure, that is to say, what component of the atmosphere consists of oxygen, we look at the partial pressure of oxygen, and we would say this is equal to the atmospheric pressure, sort of the total of all the gases in the atmosphere, times the fraction of those gases that consists of oxygen, so the fraction of oxygen in the atmosphere. So the partial pressure of oxygen in this scenario is 760 millimeters of mercury for the atmospheric pressure at sea level, and then since oxygen is 21% of the atmosphere, we multiply that by 0.21. And that gives us a partial pressure of oxygen in the atmosphere of roughly 160 millimeters of mercury. So that's fairly straightforward, and you could do the same calculation for nitrogen based on the fact that most of the rest of the atmosphere is made up of nitrogen, roughly 79%. But what if we now are looking at some liquid, like water, and we have this container that's filled with water, and it is adjacent to the atmosphere. So we have oxygen molecules above the water, like this, and we know that the partial pressure of oxygen in the atmosphere is about 160, as we were just discussing. And some of these molecules of oxygen, they have sort of this random motion that they're doing, but many of these molecules will hit the water and actually then dissolve in the water. And as more and more oxygen molecules are in the water, some of them will actually impact the surface, and they'll leave the water and go back into the gaseous state in that way. When we establish an equilibrium between the two, that is to say, between oxygen molecules that are impacting the water and dissolving in the water, and oxygen molecules that are impacting the surface and leaving the water, when those two are in equilibrium, we can now describe the amount of oxygen dissolved in the water as equal to the partial pressure of the gas above the water. So the O2 dissolved in water will equal the partial pressure of the oxygen in the air above the water. So the 160 millimeters of mercury oxygen above the water, as we described before, and that would now be the PO2 160 millimeters of mercury would be the amount that's actually dissolved in the water. That's the way we would characterize the amount dissolved in the water. So partial pressure can be used to describe what's happening in the gaseous state, but then it also tells us about what is dissolved in the liquid condition as well.